on some information measures of single-valued Neutrosophic sets and their application in MCDM problems. Abstract, information measures have received more attention in recent years. In this paper, the multi-criteria decision-making, MCDM, problem based on SVNS information measures is presented. Some definitions of information measures are first introduced. These include entropy, similarity measure, cross-entropy, aggregation operators, cosine similarity measure, subtraction operational averaging operator, correlation coefficient, and projection measure. A numerical case study, metal stamping layout selection problem, is provided in which the criteria values are described in exact, crisp, values form. Firstly, the decision matrix is fuzzified and then transformed into an SVNS decision matrix. The result of the existing methods used in this work is compared with the published results to validate the accuracy based on the same illustrative example presented in this paper and then highlights the advantages of some methods over another method. The comparative analysis demonstrates the applicability and effectiveness of the used methods. Keywords: information measures, MCDM problems, SVNS sets, neutrofication, metal stamping layout selection problem. Introduction. A MCDM problem is the process of finding the best alternative from all of the feasible alternatives where all the alternatives can be evaluated according to several criteria. In general, the MCDM problem includes uncertainty, imprecise, incomplete, and inconsistent information that exists in the real world. IFSs and IVIFSs can handle incomplete information. However, in real decision-making, decision information is often indeterminate and inconsistent. As such, it cannot be dealt with by IFSs and IVIFSs. Therefore, Smerandak 1 and 2 originally introduced the concept of Neutrosophic sets, NSs, largely from a philosophical point of view. The NSs simultaneously take into account the truth membership, the indeterminacy membership, and the falsity membership, and they are independent. However, it is difficult to apply NS in the practice of science and engineering. Therefore, Wang et al. 3 presented the notion of the single-valued Neutrosophic set, SVNS, which is a subclass of NSs. From the analysis of the literature, the information measures are very useful tools to cope with uncertainty and vagueness. On the one hand, it is known that uncertainty, incomplete, and inconsistent information exist in human decision-making. Therefore, just as FSS, IFSs, and IVIFSs, research on the information measures for SVNSs remain important. On the other hand, more and more MADM methods have been developed based on SVNSs. This paper presents some handling methods for the MCDM problem under an SVNS environment using the information measures of SVNSs. Recently, some information measures based on the SVNS set are applied to MCDM problems J. 4, 5, 6, Pen, JJ et al. 7, Liu, PD 8, Xiaohui WU19. Entropy, similarity measures, and cross-entropy are three important research topics in the fuzzy theory, which have been widely used in information fusion systems. Entropy is very important for measuring uncertain information. Since its appearance, entropy has received great attention. Majumdar et al. 10 introduced an entropy function to measure the uncertainty involved in an SVNV. Similarity measures and cross-entropy are mainly used to measure the discrimination information. Up to now, a lot of research has been done about these issues based on the Jacob, dice, and cosine similarity measures in vector space. J6 proposed three vector similarity measures between SVNSs to obtain the ranking order of all alternatives in MADM problems. To overcome the drawbacks of similarity measure J6 and J11 constructed the modified cosine similarity measures for SVNSs based on the cosine function. With the help of the distance between two SVNSs, Majumdar et al. 10 presented several similarity measures for SVNSs and discussed their characteristics. Under the single-valued Neutrosophic environment, J12 proposed a cross-entropy to establish a Mcdm method. J4 presented the correlation coefficient of SVNSs based on the extension of the correlation coefficient of IPSs and then defined the SVNS weighted correlation coefficient between an alternative AI and the ideal alternative A star. The aggregation operators are important tools for aggregating fuzzy information in decision-making problems. Two of the most common operators for aggregating arguments are the weighted arithmetic average operator and the weighted geometric average operator, which have been widely applied to decision-making problems. J5 extended them to SVNS sets for aggregating Neutrosophic information in decision-making problems. Then, the ranking order of alternatives is performed through the cosine similarity measure between an alternative and the ideal alternative, and the best choice can be obtained according to the measure values. Wu et al. 13 discussed the relationship among entropy, similarity measure, and cross-entropy of SVNS sets and their application in MCDM. As per Yang et al. 14, projection measure, PM, is an appropriate method for dealing with between objects evaluated. As mentioned in the existing literature, Neutrosophic projection models are useful methods for solving MCDM problems. They proposed three kinds of PM: general PM, bidirectional PM, and harmonic averaging PM, in the SVNS setting. In the introduced multiple attribute projection methods, the ranking order of all alternatives and the best alternative can be efficiently identified by these PMS between the ideal alternative and each alternative in MCDM problems. The bigger the measured value is, the better the alternative. Regarding existing subtraction operations of SVNS number J15 and Shigedu, et al. 16 firstly presented an SVNS number subtraction operational weighted arithmetic averaging operator, SVNS and SAAO, as a necessary complement to the existing aggregation operator of SVNS number. Next, they developed an MCDM approach based on the SVNS and SAAO for the first time. Due to its ability to easily reflect the ambiguous nature of subjective judgments, SVNSs are suitable for capturing imprecise, uncertain, and inconsistent information in the multi-criteria decision analysis. Therefore, the main purposes of this paper are to present some information measures of SVNSs and to demonstrate the application of the proposed decision-making methods. A numerical example is provided to illustrate the application of the proposed method S. Finally, the result of the existing methods used in this work is compared with the published results to validate the accuracy based on the same illustrative example presented in this paper, and then highlights the advantages of some methods over another method. Some conclusions and future research possibilities are provided. Two basic preliminaries related to SVNS sets. In this section, some important concepts about the theory of SVNSs, and some of the recent developments related to SVNS-based decision-making are recapitulated, which will be utilized in the later analysis. SVNS set model is a special case of the general NS set where the range of each of the three membership functions are in the standard unit of the interval of 0, 1, instead of the non-standard interval of -0, 1 plus. The SVNS model is one of the most commonly used versions of the NS model, and a lot of research related to SVNS-based decision-making can be found in the literature. The formal definition of the SVNS is presented below, and this is followed by the definitions of some of the important concepts and set theoretic operations of the SVNS. Let be a universe of discourse, with a class of elements in, denoted by. In MCDM problems, the initial information consists of the evaluations concerning the ratings of the alternatives concerning the criteria and the criterion weights. It can be presented by the decision matrix, which is the expert evaluation of the ith alternative by the JTH criterion. Therefore, the decision matrix will have the following form: x equals 11 12, 1, 21 22, 2, 1, 2. Any dataset sourced from unverified sources may contain wrong information, and this will affect the accuracy of the results obtained. Step 1. At this step, qualitative information is transformed into fuzzy numbers employing the vector normalization method, fuzzy decision matrix, which can be expressed as NZJ. Step 2, at the neutrosophication step, the fuzzy decision matrix, NZJ, in the crisp form is converted into the Svns decision matrix consisting of the degree of truthiness, indeterminacy, and falsehood. Therefore, the Neutrosophic decision matrix is calculated. To perform this action, the relationships between normalized values of the criteria NZJ and Svns number can be utilized. The conversion rule between NZJ and Svns numbers are shown in Table 1. B. Determine the weights of criteria. C. Information measures of Svns sets. A. Solving the case study, ranking order of the alternatives. V. Conclusions. SVNSs can be utilized to solve the indeterminate and inconsistent information that exists in the real world but which FSS and IFSs cannot deal with. Considering the advantages of SVNSs, several methods of SVNSs are put forward and used to solve MCDM problems. However, there are existing information measures as discussed in the kinds of literature to solve the MCDM problems. In this paper, the main contributions are to solve a numerical case study, metal stamping layout selection problem, in which the criteria values are described in exact, crisp, values form and to use some existing information measures to rank the alternatives. Firstly, the decision matrix is fuzzified and then transformed into an SVNS decision matrix. The result of the existing methods used in this work is compared with the published results to validate the accuracy based on the same illustrative example presented in this paper and then highlights the advantages of some methods over another method. The comparative analysis demonstrates the applicability, effectiveness, and rationality of the used methods. In the future, according to the different requirements in the real-world applications, how to optimize some information measures could form the scope of discussion and further detailed study.